There's always a first.
Go for a record.
Who's the reading?
Drop like the worst 8.
I'll just throw it all away and say, screw it, I'm just going to give you guys all A's. And all right, well, the little monitor is telling me that we need to get started, so I hope that you didn't find the exam to be too difficult last night. I tried to make it very much core concepts, and I haven't looked at them at all. I mean, like I was mentioning to the guys earlier that I've been running around like crazy since the end of the exam, transporting a cord of firewood and running my chainsaw until like 9:30 last night, annoying my neighbors and all that kind of good stuff. So, yeah. So I think my plan is going to be that shortly after class, I'll stick around for most of my office hours, and then I'm going to head home and try to do the grading, get it out of the way, and let my puppy run around a little bit more. So, yeah. So expect a quiz tomorrow at the end of class. It'll probably be something either power related or just AC circuit related. I did post a homework assignment that covers both the last chapter and this chapter. 10 total questions, and so I think I was looking at the calendar. I'm going to guess something like Monday or Tuesday next week. But I tried to, again, kind of pick the core questions, and it was 12 questions, and I was like, oh, I want all 12 of them, but I took out 2 of them. So you've got just 10 total questions. So, yeah, so look something like Monday or Tuesday for that assignment, and then probably give you one more short homework assignment to be turned in just before the final. So I think they've posted the final exam schedule. I haven't looked at it, so I don't know. Have any of you guys looked?
I think it's
10 o'clock on Friday? In here or someplace? Let's see if we can find that out real quick. It's not like it's a big deal. Is that the summer one? So let's see, we are WE2110, 8:15, 10 o'clock in the morning, in 214 in building 28. What is building 28? It's Becky? Okay. So upstairs a couple floors. I guess 2 hours, all that kind of good stuff. So that shouldn't be too bad. We should be pretty much ready to go, and it'll be interesting to see exactly how far we get in the material. I was looking at, we might actually get to the point where we're going to get to some of the early Laplace transforms and frequency response stuff, and perhaps get further into that than I've ever gotten with one of the circuits classes before. So last summer I drove people pretty hard, and I ended up just taking the last day and saying, hey, it's you don't have to come if you don't want to, and it's all review, all questions, just come. And we did it outside of the studio classroom and everything, and I was really expecting nobody to show up, and like 6 people showed up for an optional review day. I was astonished. But yeah, are there any questions before we get started?
Everybody showed up with slides.
Okay, well, let's take a look at and kind of review the stuff that we talked about on, I'm freaking out the camera guy, because if all I have to do is move over a little ways this way, and they have to move to a different camera every time I go back and forth. So let's review the stuff that we talked about on Monday. So we were talking about steady state power and AC power. This is where it gets somewhat more interesting than just the simple P equals VI kinds of stuff. But we do have at least four different kinds of power that we will think about primarily as we're going through this. And each one has its place. It's not like one of the powers is the right kind of power. We look at them and they have different applications and different uses. Instantaneous power is the easiest one. It's the simplest. Just kind of, we know that we have this sinusoidal waveform for the voltage. We have another sinusoid for the current. We multiply them together, and that will give us the instantaneous power. But it's a function. It's just another sinusoidal function, and that's not always helpful. So we can sometimes we want a number. Just want to give me a number. 12 watts. 1.21 gigawatts, whatever, just give me a number, and average power will give you a number. To some extent, average power is still somewhat, it's not unuseful, but one of the more useful ways of talking about it is root mean square power or RMS power. Using those values is more common than using the peak values. So we're used to thinking about the 120 volts that are at the wall sockets, but that's an RMS value. We're looking at 170 volts approximately at the walls as a peak value. What we will get into today that we didn't talk about yesterday was power factor correction, and how that relates to something called complex power, where we separate out the real power from the reactive power and how all of that works together. So again, instantaneous power gives you a function, and it's just simply doing the math of multiplying the voltage times the current, and what you end up getting is this sinusoidal waveform where you have the magnitude of the voltage times the magnitude of the current divided by 2 times the cosine of the angle, the difference between the phase angle of the voltage and the current, and then another cosine term of 2 omega t plus the sum of the two phase angles. So what that gives you is one DC component. The cosine of the theta v minus theta I is going to be a constant, and then you have a sinusoidal waveform at twice the frequency of the original input frequencies. So calculating instantaneous power is just a matter of kind of plugging numbers into that formula and seeing what it gets you. Average power, it takes the instantaneous power over some period of time, and what we normally choose as our period of time is one period of the sinusoid. So that what that means, as much as anything, is that for reactive things, it kind of goes away. You have some that's on top and some on the bottom. You add them together and it goes away. And so the reactive circuits essentially goes away. For purely resistive circuits, the cosine term goes away because the voltage and the current waveforms are going to be in phase, and the cosine of 0 is 1. So you just have power equals 1/2 Vm times Im. So those are the simple ones. The one that you should remember and try to keep in your minds is going to be the 1/2 Vm Im times the cosine of theta v minus theta I. At least like final exam time, that's the kind of thing that you would see on the formula sheet. So it's up to you to kind of remember that, what the difference between the phase angles is going to be. Yeah. So in general then, what that means as much as anything is that for the average power for a purely reactive element or an inductor or capacitor specifically, the average power is going to be 0, but that doesn't mean that you can ignore those reactive elements, because they do change the phase angle relationship between the voltage and the current, and so that's going to change what exactly the average power is that's being messed around with in the circuit. The next one that we're concerned with was effective or RMS values. RMS again is root mean squared. Average power is useful, instantaneous power is useful, RMS I think is the most common. I think that's what you're going to see the most is if you were to be pursuing the power option. And I remember, at least in my power classes, using RMS values quite a bit and not so much of the complex power. But kind of the idea is how effectively are you transferring the power, or how can we kind of relate this to a DC power if we could do that. So that's what RMS values give us. The way of calculating that, again, I mean, you kind of work backwards. We call it root mean squared, but what you really do is you do the square, then you do the mean, then you do the root, and that's what gives you the, allows you to calculate it. So first you'll square that function, or you square that value. You integrate over a period and divide by the period, which gives you the mean, and then you take the square root of that. That's how you'll calculate it in general. I think for the most part, your rule of thumb and what you'll do most of the time is just if you have a peak value, you'll divide that by the square root of 2. If you have an RMS value and you want to find the peak value, you just multiply by the square root of 2, and that will give you the other one, whatever you happen to be looking for. So RMS, I think, is pretty typical. If you were to, I think if you pull off if you look at the top of a light bulb, a standard incandescent light bulb, you should see something about 120 volts RMS, and potentially talking about the, and so, I mean, they're expecting, they are quantifying this stuff in terms of RMS values and not in terms of peak values. We did at least one example of calculating RMS from a waveform. I deliberately did not choose any of those questions in the homework assignment because I just think that they're ridiculous and kind of trivial. But we did at least one example to show you, what it looks like to do it. So this is about where we got to. We started talking about this concept of the power factor, and we took the average power definition. And when you take and you replace the peak values with the RMS values, to make that happen, you put in so it's the RMS value times the square root of 2 for the voltage, and the RMS value times the square root of 2 for the current. Those square roots of 2 multiply together and cancel out the 1/2 in the average power definition. What it brings you to is your average power can also be expressed in terms of RMS values. And so you just take the RMS voltage times the RMS current, and then multiply that by that cosine term, and that will give you the average power as well. So if you just have the RMS values, you can calculate average power as well. To differentiate it from average power specifically, we will talk about it primarily as apparent power in terms of voltamps instead of, or voltamperes specific, more fully, but normally just call them voltamps. And that's the apparent power. And we'll continue to see usages of voltamps, especially when we get into complex power. They still use voltamps. The cosine term is a dimensionless quantity called the power factor, and the power factor becomes very important as we start looking at industrial loads especially, but also even in residential loads exhibit pretty bad power factors sometimes, because as we'll kind of see this in just a little bit, but I think in general what you're going to see from most of the loads that you have at your house, or you have hooked up in some big factory, they're going to be primarily inductive loads, because things like a blender, a microwave, well, I'm not sure about a microwave so much, but refrigerators, anything with a little motor in it is going to appear to the power system to be an inductive load, because it's more or less an inductor when it the windings on the motor. And what that ends up doing is it causes a lagging power factor, and we'll kind of see the ramifications of that what it actually requires then to supply the needs of your house is the worse that power factor gets, the more power the substation or the power generation facility actually needs to create. And that costs them money, it costs us resources, and then it shows up on your bill as you using a lot more power than you necessarily want to. And so it becomes advantageous, especially for heavily, heavily inductive loads. I don't know that you're ever going to find your house being, even if you were running like lots and lots of ceiling fans and you had 12 refrigerators for some reason, I still don't think that you're going to be approaching the kind of inductive loads of some sort of major industrial factory of some kind. But still, the bottom line is you're going to want to think about trying to fix that power factor because it will save you money. And I think last summer I looked up power rates, and it's thousands of dollars a year that you can be saving. And I forget, it was getting up, I think, into like the tens of thousands of dollars per year for fixing some of these power factors and getting them closer to unity. So the power factor is the entire cosine term. The power factor angle is the difference between the phase angle of the voltage and the phase angle of the current. To kind of expand on the power factor stuff, we can be looking at phase angles. The power factor angle can be anywhere from, in terms of a magnitude, from 0 to 90 degrees. But that can also be, from realistically from negative 90 up to positive 90, depending on whether you've got a primarily inductive or primarily capacitive load. So the power factor then, because we're just popping that into a cosine term, should be somewhere between 0 and 1. There's no scaling, no magnitude changing here. So it's just going to be somewhere between 0 and 1. A unity power factor is kind of what we're shooting for, and that indicates that either you have an entirely resistive load, an entirely real load, or you've combined things properly in your RLC circuit such that you've approached that unity power factor. And what that kind of means is that you have enough capacitance in the circuit to offset all of the reactive needs generated, or the reactive power that's being absorbed by the inductors. Because you get these different power factor angles based on whether you have a capacitive load or you have an inductive load, we have to specify not just what is the magnitude of the power factor. I can tell you, okay, yes, my power factor is 0.84, but that's not complete information. Just like we need to give our voltage a magnitude and a polarity, we need to give our power factor a magnitude as well as indicate whether it's leading or lagging. And the more common one is to see is a lagging power factor. You get lagging power factors when the load is primarily inductive. So we define the power factor lead or lag as in respect to the current leading or lagging the voltage. And so when you have an RC load, a capacitive load, that means that it creates a leading power factor, and an inductive load creates a lagging power factor. So that's what we're shooting for primarily. We'd like to get, again, that unity or one power factor. Whether we can actually achieve that or not is kind of up in the air, but that's what we're at. And then we'll talk in a little bit about how to correct power factors, because it's nice, to be able to quantify what is our power factor and what is how does our specific inductive load contribute to that power factor, but we'd like to be able to do something about it too. And so in a few slides we'll talk about how to correct those power factors and get them closer to a unity power factor. For now, let's start taking a look at an example or two and stop just yammering about the power factor and doing something with it. What's kind of interesting when we get to this point in the class is we start almost getting away from circuits to some extent. We can draw a circuit of what this situation looks like, and it doesn't hurt to do that, but so in theory, this is what our circuit looks like. We have some sort of voltage source, and in this case, that's like the power, the substation or something. We have some transmission line impedance, and it happens in this case to be purely resistive, and so it's just going to be a resistor that we're going to modify or model here. And then here's kind of the walls of our factory. And we have some sort of load. And we're not going to try to characterize it as anything specific. We're just going to say we know that we happen to be consuming 88 kilowatts worth of power. And we know that our power factor is 0.707, and that's a lagging power factor. And so one of the things that we would like to be able to figure out here to some extent is what is the power. Well, the first thing that we want to find out is what is the, one more thing that we need to indicate. The voltage across the entire load here is 480 volts RMS. So that's one thing we need to be aware of is we are going to be dealing with primarily RMS values, again, from here on out. So the first thing that we'd like to know is what is the RMS current that's supplying this particular load. That's the first thing that we would like to kind of see. And it's one of the important things. So this was a 0.08 ohm resistance, and we don't know exactly what our source voltage is. We know that in terms of what it's delivering to the load is 480 volts, but that's some fraction of what is actually being supplied or generated at the substation or whatever. So we'd like to know what the RMS current is first. And so we'll kind of go back to our average power formula, which said that the power, and we'll write it in terms of this one, the power of the load is going to be equal to the RMS voltage times the RMS current times the cosine of theta V minus theta I. And for this, it's kind of important to remember that, hey, that's just the power factor. So we have the power factor, we have the result of that cosine term, we have the RMS voltage, and we have the real power, or the apparent power that's being consumed by the load. So we have everything except for the RMS current. So we just need to rearrange the terms and solve a little bit for this. So if we do that, the RMS current will equal the power that's being consumed by the load divided by the RMS voltage divided by and multiply that by the power factor itself. So we know that that was 88 kilowatts divided by 480 times 0.707. Just double check my math here. 88 kilowatts divided by 480 times 0.707 gets you 253 or 259.3 amps RMS. So that is so the other thing that we would kind of like to so we now we know what the current is, and now we kind of like to think about what is the power that is actually being generated by the substation to deal with the load that we are imposing on it. And this is where it actually gets fairly interesting. We know that the total power that's going to be generated by this circuit is going to be whatever power is being delivered to our load plus whatever we're losing in the line. So we can call that P line or P loss or whatever you want to call it. But that's part of the reason that we solve for the current in the first place, is we'd like to know what the losses are in the line. So we know what the power that we're consuming at our load is. That's 88 kilowatts. but the power that we're losing in the line is going to be dependent on the current draw of our load. So that's going to be I squared times the resistance, or 259.3 squared, times that 0.08 ohms of resistance. 259.3 squared times 0.08 is 5378. So add that onto our 88,000 watts that we had before, and we get a fairly large number. In terms of, just making it kilowatts, that's 93.38 kilowatts. The full number is very close to 93,379-ish watts. And so that's what the power station is actually generating for this particular application. And I think this is the kind of thing that they might actually be charging you for. You're getting charged to some extent for the 93,000 watts that your load is essentially causing the power station to create. So let's say the magic power factor fairies come fluttering into our factory and change things a little bit, such that instead of having a 0.707 lagging power factor, now we have a 0.9 lagging power factor. How does that change things? How does that change the total draw of power here? So we can just redo some of this math. It's pretty straightforward. The RMS current for our new power factor is going to be the same equation. Divide the RMS, or divide the power by the product of the power factor and the RMS voltage. So that'll be the same 88 kilowatts. Most of these numbers don't change. The 480 volts remains the same, but the power factor is now 0.9. So we divide our 88,000 by the product of 480 and 0.9. And that gives us 203.7 amps RMS. So that's nice, I suppose. How does that change the power that's in our line here? Well, the power that's being totally generated by our source, again, is still equal to the line power plus what's being lost, the load power as well as what's being lost in the line. It's still 88,000 watts for the load, but now we're down to 203.7 squared times that 0.08 ohms of resistance. So we crank that into the calculator, 88,000 plus 203.7 squared times 0.08. And you get, specifically, you get 91.319, or 91,319 watts, which is about 91.3 kilowatts. If we wanted to extend that, we could make it 91.32. And so now we can take a look. Let's see if we can get both of these on the screen at the same time. Here was the total power that was being supplied by the substation or the generator before we changed our power factor. And here's what it is now. We've reduced our load by 2 kilowatts. And if you start, multiplying that by 24 hours a day, 7 days a week, that becomes considerable. It's no small amount of power that we're saving by doing that, by fixing that power factor. The question that we still need to kind of answer is, how do you fix that power factor? And we'll look at that in just a minute. Why don't you guys try this one? I will write up the problem statements, and then I'll put this work back up. But you guys can take a look at this one. We have a load that is consuming 100 kilowatts of real power. The power factor is 0.707 lagging. The 60 hertz voltage is 480 at an angle of 0 degrees. Volts RMS is the voltage at the load. And in this time, the line impedance is 0.1 ohms. So what I want you to do is determine how much power is saved if the power factor is magically changed to 0.94 lagging. So it's a lot of the same kind of work that we just did. So I will put this version of it up. And so take a look at that and try to run those numbers. Find out exactly how much power is saved if we change that power factor from what it is now. Take, I don't know, 4 or 5 minutes to look at that. looks like most people are getting pretty close to being done. So let's walk through this and see. You guys can please shout out answers for me. So what is the RMS current of the original version of this circuit? How much?
294.6.
294.67. So what is the total power that's being generated as a result?
108.68.
Yeah. Sure, we can do it as kilowatts. 108 kilowatts. So that's our total power. So this is the old case. In terms of the new stuff, what is the new RMS current?
231.
231?
Oh, sorry.
I have a slightly different number. Yeah, I have 221 in my notes, but we can divide 0.94 times 480. Yeah, I get 221.63. So 221.63 amps RMS. So what then is the total power that's being consumed in the new case?
104.91.
Yeah, it's fine. Boy, I'm such a good sideways writer. So what is the overall savings?
3,771, I guess.
Yeah, about 3.77-ish kilowatts. So I suppose that in some ways that shows the value of significant digits and all that stuff, but man, there's nothing I hated more than dealing with sig figs. Man, it was just awful. Okay, so that's a little bit of power factor stuff. We will come back and revisit that in just a minute after we've taken a look at this idea of complex power. It's the last different kind of power that we're gonna talk about. So, did I fix this next one? No. Okay. So looking at the slides, what we would like to be able to do is represent and discuss not just the kind of the real power, but also the reactive power that's being consumed and absorbed, I guess absorbed and supplied to the circuit. And occasionally what you will see reactive power called instead of reactive power is the quadrature power. To some extent that gives us, we'll talk about it as being, we'll assign that to a variable called Q, and so to some extent that's why we assign it to Q. And if you take the electric motors course, you'll see a lot more of quadrature has a lot to do with electric motors. And so what we do to define the complex power is we define that as S. We assign the complex power to a variable called S, and we multiply the RMS voltage, and that is I would like to change that color. This is a phasor. This is not just the magnitude, but this is the phasor. We multiply the phasor RMS voltage by the complex conjugate. Don't forget this little star up here. I think at some point you will all forget the little star. I forget the little star sometimes. Don't forget the little star. It makes a big difference in calculating the RMS because we're not just using the RMS current. We're using the complex conjugate of the RMS current. And what that means, practically speaking, is that, for example, down on the bottom, we've taken the magnitude of the current and multiplied it by the negative phase angle. the other way of thinking about that is if you have a number like, let's see if we can do this reasonably, a plus jb, the complex conjugate, if that's, say, we've x equals a plus jb, then x complex conjugate equals a minus jb. So these two things, this idea of a negative phase angle or changing the sign of the complex quantity, they have the same idea. And so those are the ways that you'll deal with that. When you start multiplying out to find the complex power, do not forget to take the complex conjugate of your current. Or if you're given the complex power and an RMS voltage, don't forget to take the conjugate when you're telling me or somebody else what the actual current is. Don't forget it. You'll want to, but don't. And so, in other words, you just go ahead and you, if you want to calculate the power and you have everything, you can just say, well, multiply the magnitude and the magnitude of the voltage and the current, and then put it at the angle between them. And obviously, this should look familiar because that's just the power factor angle. So that's just to remind you and see, you have seen this quantity before. Next. So what we will, and I don't know why, again, this is just another convention, I suppose, but we are almost always going to talk about power, or this rectangular complex power, in terms of a rectangular form. So you calculate it using a bunch of phasors, and then you give me the answer as in rectangular form. I was noticing in my notes that for some reason, in like 2.5 or 3 years, I've still never fixed the fact that this slide says rectangular complex power. How many times do I have to see this mistake before I fix it? But I think the reason in this case that we do go ahead and use the rectangular form is to make it very clear what is the real component, what is the reactive component, and here's where you see that Q thing pop up. And so we've got the real power, and then we've got the quadrature, or the reactive power. I will almost never call it the quadrature power. It just doesn't exactly roll off the tongue or anything like that. So I almost always call it just the reactive power. Calculating either part of that, you multiply the, if you want to if you have everything and you want to know what is the complex, what is the real power, then you can multiply it out in a very straightforward way. And that's, obviously this is just our average power formula for the real component. For the reactive component, you take the sine instead of the cosine. The second bullet point here is different on your notes. I had to fix this even this morning. That's another problem with this slide that somehow never gets fixed from semester to semester. We measure complex power, and all of the answers for complex power will be measured in volt amps. I was just double checking some of this stuff, and there is no real difference between a volt amp and a watt. They are the same thing. But just to make sure that people are aware, this is what we're talking about. We will express complex power in terms of volt amps. If I ask you what is the real power, what is the P component, or what is the Q component, the apparent power P is measured in watts. It's real power. It's just watts. And the reactive power, the Q, is measured in volts amp reactive. And I will almost always just pronounce that as VAR. I like to read acronyms whenever I can. So, yes, that's rectangular complex power. So I think we've got some examples of trying to, or there's some practical conclusions that come out of all of this stuff. If you start plugging what we know about resistors, inductors, and capacitors into these formulas, you get some sometimes interesting results. The resistor, there's nothing, I think, particularly surprising here. It's all very kind of straightforward. the voltage and the current are in phase, therefore the power factor is 1. The sign is 0, so that's just, this is calculating P, this is calculating Q for the resistor. So P is some number greater than 0, and Q equals 0. It has to. And so what that means is that a resistor absorbs real power and there's no reactive component whatsoever. If we pop in the values for the inductors, the phase angle difference is going to be a positive 90 degrees. That means that the P value is going to be 0 and the Q value is going to be some value greater than 0, whatever that value happens to be. And since it's a positive number, it's going to be absorbing the reactive power, but there's no real component to anything that's happening with the inductor. Now, what gets, I think, the most interesting part is that when we start looking at the P and Q for the capacitor, because it's a negative 90 degrees, that's interesting. Our passive sign convention says that if you see a negative power, well, that means that it's being supplied to the circuit. And that's what happens. When you calculate this sign, the sign of negative 90 degrees is negative 1, and so the P value is 0, so there's nothing real. But because the Q value is less than 0, it supplies reactive power to the circuit. And that's the whole idea behind power factor correction, is that you have an inductor that has these needs, these reactive power needs, and instead of forcing the power system to do that, we're just going to stick some capacitors into the circuit, and that's going to supply the reactive power needs of your inductive load. And it's pretty cool that that happens, I think. It might be the most interesting part of power for me. So it's interesting when you start thinking about what happens with the complex power of each one of these circuit elements. So we'll get rid of all that. Here's something that in the past I have occasionally glossed over, and I think it's worth mentioning because if for no other reason, it occasionally shows up on prereq exams and whatnot. It's something called the power triangle. And the idea here is that we have, if we start plotting out the values of our complex, our real, and our reactive power, the relationship is a right triangle. And the relationship is on the screen. We can put it also on the paper here and when we start thinking about it. But if we take the tangent, and obviously this is just, again, the power factor angle. If we take the tangent of that power factor angle, that gives us a relationship between Q and P. And this is just good old SOHCAHTOA at work, right? That if you take the tangent, that gives you the relationship between the opposite and the adjacent, right? Yeah, opposite over adjacent gives you the tangent. And so what we have is this triangle. And so this is obviously the right angle of our power triangle. This is the real power P. This is the reactive power Q. Make sure I'm getting that right. Yeah. And this is the complex power S. Conveniently, this angle here is the power factor angle. And so we've got some nice relationships, and we can start calculating things based on based on these relationships. So if you happen to know what your P and Q values are, you know what the tangent is. You take the inverse tangent. You can find your power factor angle. and then you could find out what your power factor is by taking the cosine of that, and so on. And this relationship can be vaguely useful to you. It's one of those things that I think for the most part, in terms of my own getting through this class, teaching it, and getting through the material as a student, I never really used the power triangle that much. But it's something that I want to make sure that you guys have seen, because I got enough questions about it after the first time that I taught the class. So this is probably the most valuable relationship from this stuff, that you'll want to know that. And if you ever just kind of forget it, you can start thinking about, good old, SOHCAHTOA, is that right? The sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So opposite over adjacent gives you the tangent of that angle, right? So just remember that, and you can always derive it if you can't remember this Q over P bit. And we'll use that in order to find some of these values that we want to. So this is where it starts to get perhaps a little bit nasty. If we know the voltage and current, and we want to calculate power for some sort of impedance, and the impedance is going to be some phasor Z at the power factor angle, which is that same quantity that we talked about a while ago in terms of complex impedance, where you've got the real part R and you've got the complex portion X. There are essentially two ways to do that. Determine what the phasor values V and I are, and then calculate the normal ways of just going through it. Say BRMS times IRMS, and then take the cosine, find out the power factor. And that'll tell you at least what P is. You can always also use the I itself to calculate the real part of S as an I squared R thing. It's not well explained in the textbook, and so I tried to look at it some more this morning to figure out what exactly was going on. But this is important to realize that you're going to want to rely more heavily on the I squared R version of the power in terms of figuring out what the real component of the complex power is, because if there is any reactive or complex impedance at all in your circuit, in other words, if X is not equal to 0, then you cannot use V squared over R to calculate the real components of the power. So kind of just forget that one exists, and just use I squared R. So if you do that, and it's important again it's hard perhaps to see, but this I is a vector, or is a phasor. This I is just a magnitude. So you multiply the magnitude of the current times the resistance, and that will give you the real components of your complex power. And so if you have some of this stuff, once you have the magnitude of your current, you can square it, multiply it by the overall impedance, and that will give you the current. Or once you have P, you can always go back to that tangent of the PF angle equals Q over P. You can always use that too to figure out what's going on. So we got some examples. Let's do maybe just one example and call it good for the day. So before we get into power factor correction and stuff, and that's probably a good stopping point anyways. So here is our lovely, lovely circuit. we have now a complex impedance in our line. It's not just a real impedance anymore, but we have now what we still don't know what the source voltage is, but we'd like to figure out what it is eventually. Very small impedance in this line, but you've got both inductive or reactive impedance as well as the real impedance. Then we have a load, and that load is known to consume 20 kilowatts of real power. That is P. It's not explicitly stated in most of the problems when you redo the homework or something, but when you see something in watts, you should think, well, that's a P value. It's not a Q value. It's not an S value. It's got to be a Q or a P value because it's being expressed in watts. And we know that this has a 0.8 lagging power factor. The last thing that we know is that the voltage across this happens to be 220 at an angle of 0 degrees RMS. So this is going to be, I think, the fairly normal way of going about and doing this, and I've never run into any problems kind of using this. It's almost a cookbook methodology of determining what's going on with complex power. So one of the equations that I don't know that we've necessarily seen before, but you're going to want to use, I think it's going to be extremely helpful for you, is to say that the magnitude of S is equal to the magnitude of P divided by the power factor. That's, I think, just another trigonometric identity, essentially, just taking the power triangle and applying it. So that's going to be extraordinarily useful for you. So we can start plugging in those values. We know that that's 20,000 watts. We divide that by the power factor of 0.8. And so that tells us that the magnitude of S is 25,000. So we'll kind of stick that aside when we start thinking about what is, at least when we start thinking about the phasor representation of S, it would be 25,000 at some angle. But what that angle is, we've still got to kind of figure that out. But this is the magnitude, 25,000. What we need to do to find out what, so that's the magnitude. To find out what S is itself, and it's really hard to make this look bold-faced, but it's going to be 25,000 at some angle theta. But what is theta? Well, we just take the inverse cosine of the power factor, and that tells us what theta is. I guess I was trying to think if there's something more that needs to be explained with that, but it's just if the power factor is calculated as a cosine of an angle, if you take the inverse cosine, you get the angle back, I suppose. And so that's going to be the angle of your complex power. So we take the inverse cosine of 0.8, and you get a value. It's not a particularly pretty value. It's 36.87 degrees. 36.87 degrees. And so our complex, our phasor representation of this complex power is going to be 25,000 at an angle of 36.87 degrees. And now all you have to do is you can say, well, now give me that in rectangular form, and that will tell you what your complex power is. So 25,000 at an angle of 36.87. In rectangular form, you get 20,000 plus J 15,000. Now here's a bit of a sanity check for you, okay? This is supposed to be P plus J times X, right? We know what P is. P is supposed to be 20,000. We still have 20,000 as our P value. Good news. We haven't done something weird and lost, messed up our values. So that's something to kind of bear in mind, use as a sanity check for your work. Okay. So then, if there's going to be some current, phasor current that's running through the line, and we can calculate that now that we know what the voltage is, and what the voltage is across this load, as well as what the complex power is. We finally have that down here, so we can calculate what that current actually is. Here's one of the first places that you can screw up and say, oops, I forgot to take the complex conjugate of my current when I was doing my work. So make sure you take the complex conjugate of the current. Our relationship says that S equals V RMS times I RMS star. So what that means, we can rearrange that because we have S, we have V. We would like to solve for the line current, which is going to be the RMS star part here. So the line current complex conjugate equals the complex power divided by the voltage. So that's going to be 25,000 at an angle of 36.87 divided by the 220 volts at an angle of 0. So put that in, 25,000 at an angle of 36.87 divided by 220 at an angle 0. Whatever. Express that as a phasor for convenience sake, I suppose. It's a current, so we kind of like to do that. And so that is 113.63 repeating at 36.87 degrees. Now, before you go and use this quantity to do anything else, like what is the power lost in the line or anything like that, stop and say, I have not yet taken the complex conjugate of the current that I just solved for. So, before I do anything else, let's find out what the real line current actually is, because it's going to equal 113.63 at an angle of negative 36.87 degrees. Don't forget to take the complex conjugate. And that is an RMS value. Okay, so next part, we would like to find out exactly so part of what we're trying to do here is to find out, because when we first looked at this problem, one of the things that I never told you is what is the input voltage V sub S? We didn't say what that was. We'd like to find out what that is. And what we'd also like to know is what is the power factor at this point in the circuit? We know what it is over here, but we would like to know, including the line resistance, what is the power factor. So that's what we're trying to solve for, and that's why we're doing all of this work in the first place. So now we have what the line current is, and we can find out what the complex power is that's being absorbed, that we're losing in the transmission. So let's call that the loss current, or the loss power. And that's going to be I squared times Z. That one's a phasor. This one is a magnitude. So maybe, if that helps, we're dealing with a magnitude here, and not the whole thing, just the magnitude of the phasor. So that's going to be the 113.63 squared times the total impedance, which is just the 0.09 plus J 0.3 ohms of resistance. Oh, I guess impedance total. So 113.63 squared times 0.09 plus J 0.3. Put that as a phasor. Well, I guess we probably don't want to do that. Looking at the real and reactive losses, we've got 1162, and drop it there, plus J 3873. Really it's 3874, if we're going to be consistent in our rounding. And you can obviously take that out to more decimal points. In my notes I have. So the total power that's being generated, again this is I think more of an aside than anything else, is going to be what's being generated or consumed by the load plus what's being lost in the line. And we had calculated that the load was consuming 20,000 plus J 15,000 volt amps. This is an S. So this is supposed to be S from the source, not P. Plus what we lost in the line, this 1162 plus J 3874. And the number that I have here is 2162, 21,162 plus J 18,874 volt amps. And that should be, these are volt amps everywhere that we look at these complex power things. So that's more of an aside than anything else. There's not a ton. I mean, it's perhaps interesting to know that that's the case, but whatever. It's not a huge deal. Actually, it is useful to know. If we convert that to a phasor, that will give us the magnitude of the power, which is going to be 21,162 plus J 18,874 is 28,356 at an angle of 41.72, actually 73 degrees. So we're going to use this part. We're not going to care so much about the angle, but we're going to use that because the voltage at the source is equal to, we're going to multiply the voltage times the current. But if we just want to know the magnitude of the voltage, say, well, it's the magnitude of the power at the source divided by the current that's running in the line, but again, the magnitude of the current. And that's going to give us the magnitude of this voltage. So 28,356 divided by, up here, 113.63. And that gives us 249.53 volts RMS. So that's the magnitude of that voltage. But if we want to know what the phase angle is, I think, I forget what that one is. Do we need to know the I forget what the the phase angle of the voltage is going to be. How do I count it? Shoot. I have a random number here, and I'm not sure where it came from. That's what we want to try to figure out, because we need that for a couple of reasons. One is that we need it to figure out what's going on in terms of the power factor, but we also need to figure out, we'd like to know what the whole phasor voltage is. And I'm drawing a complete blank on how we get this. It's not the phase angle of the... See if I can grab a hint and get my mind back in gear. Okay. This gives us the magnitude, but we can also, it's just actually a simple KVL around the loop is what will give us totally what's going on. And so perhaps this is even more of an aside. The total voltage at the source as a phasor will be equal to the phasor voltage of what's being lost as well as the phasor voltage of what's at the load. We know that this is 220 at an angle of 0 degrees. It told us that in the problem statement. What's being lost is going to be the phasor current here, this the line current times the impedance, the line impedance itself, which is hardly going to fit. The loss equals I line times the where to go number, small number, 0.09 plus j 0.3. So that was 113.63 at an angle of negative 36.87 times 0.09 plus j 0.03 or 0.3. So the loss is 0.6 at an angle of 36.43 degrees. So put that in over here, 35.6 at an angle of 36.43. And add those two together, plus 220 at an angle of 0. And that means that the source voltage needs to be 249.5 at an angle of 4.86 degrees. So this is our theta V. Very quickly, last thing, what is the power factor of this whole thing? The power factor is the cosine of theta V minus theta I. So that's the cosine. We just calculated theta V as being 4.86 degrees. Earlier we calculated theta I as being negative 36.87. And so that equals 0.746 lagging. We'll do a little bit more of this tomorrow. I'm going to plan on getting your exams back to you. That's going to be my goal for today. And if you have any questions, let me know. Have a good one. See you tomorrow.